May 1952, when it pioneered the world's first jet passenger service. On its first flight from London to Johannesburg, it created new records. Its performance thrilled the world and added a new chapter to the shining story of British aircraft and British airmen. Since then, the Comet has blazed new trails, achieving new speeds, setting a new standard. After 12 million miles of flying, and with confidence firmly established in the Comets, it was with dismay that we learned that Yoke Peter, the first of the Comets, had crashed into the Mediterranean off Elba with the loss of 35 lives. Yoke Peter took off from Rome Airport on schedule. A few minutes later, the plane exploded. Ships of the Royal Navy hastened to the spot, but there were no survivors. Immediately, BOAC grounded all Comets and the search began for the wreckage. Thus, the most extensive investigation of its kind ever held was started.
So, what we talked about before was all about figuring out exactly what the fluid pressures would be in a fluid at a point. So if you go up in a fluid or down in a fluid, it matters whether it's a liquid, right? If you go up or down, the pressure changes by the elevation change multiplied by the unit weight. Actually, it does in a gas as well, but in a gas it doesn't really matter so much because the change is relatively small. And so those are the reasons for our so-called the manometer rules that we have. If you go up, you subtract the pressure change. If you go down, you add a pressure change, it adds. If you go horizontally, on a horizontal plane, the pressures don't change laterally. If it's evacuated, then the vapor pressure is the pressure that exists in the cavity. And if you go up and down in a gas relative to a liquid, then the unit weight is so small, typically a factor of 1,000 times smaller than a liquid, that perhaps we can think of the fluid pressure being the same all the way through. So those are the rules that we dealt with. So now what we'd like to do is we'd like to use that for some utility. And so the utility for us is to be able to figure out what the pressures are, not just at a point, but applied on structures. And so we try and give some rationale as to why we might do this. And so our rationale initially, from what we're talking about, would be, for instance, why do we need to know this? Well, we need to know this because fluid pressures on structures affect the integrity of those structures. And those structures can be a variety of things. They could be airplane fuselages. And so the video that was playing previously was of the Comet. See if we can zip right to the end. So post Second World War, 1950s, everything coming out of this 1945 were basically turboprop planes, like the ones you fly out of State College. Actually, the turboprop plane you fly out of State College is a de Havilland Dash 8 or Dash 7. Same company as this, the de Havilland Comet. Beautiful plane, really. In the early 1950s. Jet engines in the wings, not a style you see today. But it flew for a while, and all of a sudden they just didn't. They stopped arriving at their destinations. And they stopped arriving at their destinations because they broke up in flight. And what happened was that before we understood completely about the idea of fatigue, so you take a piece of metal and you bend it and bend it and bend it. It doesn't break the first time, but after the 1,000th time or the 10,000th time, it fractures and breaks. And that's exactly what happened with these airliners, was that you fly to 30,000 feet. We know that the pressures at those are much lower than at sea level. The cabin is pressurized to sea level pressures, and therefore you pressurize the cabin, you depressurize it. Pressurize it, depressurize it, each time you go up and down. And so these things started disappearing out of the sky, and what it was found was that there were fatigue cracks that were developing, and this is a rig to be able to load it, you'll see in a moment, pressurizing it on the outside, I guess on the outside, to be able to, or perhaps pressurizing on the inside, right? Put a fluid in it, blow the fluid pressure up relative to atmospheric. All that matters is the difference between the internal pressure of the cabin, which is overpressured now, relative to atmospheric outside. You get the same differential, and you can do that over and over again until it finally fails, and you proof test it to be able to figure out exactly what the problem is. Interestingly enough, much more recently than this, there was an example of a Hawaiian Airlines, a flight that used to hop between the islands. Again, multiple pressurization and depressurizations, because it would make, 20-minute flight, it would make 20 or 30 of these a day, and one day just the roof of the plane unzipped, I think it sucked out a couple of people, but the plane actually landed with a big gaping hole in the top. And so problem of fatigue and the pressures applied on that relate to whether it will fail or survive. And so one of the reasons that we might like to look at that is because we like to be able to fly safely. So we talked already about the Malpasset Dam. Again, dams are used for water storage, for irrigation, but they're also used for power. You block up a river, you impound the lake behind it for recreation also, but you can also use that increased head of water to run through turbines at the base of the dam to be able to generate electricity. You take the potential energy of the water up at the top. Where's my thing? The water up at the top. You run the water, which has potential energy up here. You run it through turbines by translating the potential energy to kinetic energy. You transfer that kinetic energy to a turbine, and you generate electricity from it. And if you do it wrong, as we talked about previously, Malpasset Dam, this is in the south of France. This was a curved arch structure. So originally the arch would have gone across the whole valley, impounded on this upstream side a dam behind it. And in the 1952, it failed and killed 400 people by the wave that went downstream. Around the same time, early 1960s, the Resultant Dam, which is in the Italian Alps, not the French Maritime Alps, had a similar failure, a beautiful arch dam, which still survives today. But what happened was there was a landslide on the slopes, rainfall activated it, creeps down the slopes, accelerates, drops into the reservoir like throwing a stone into a lake, and all the water that was in the lake was displaced by the former rock slope that was landing in it, and a wave of water went across the top of the dam, didn't destroy the dam's still intact, but now holds a reservoir full of rocks, and the wave traveling downstream washed out of a number of villages in these tight valleys. What else? Let's try this one as well. So this is also in, so this is the Dam Busters, or the Bouncing Bomb. I'll shut the volume off so you can hear me. And so this is Second World War, German war effort in the middle 1940s. I'm not sure, 41, no, 42, 3, 4. And the key to production for the war effort was in the factories producing whatever they produced, tanks and armaments. And so one way to deal with that is to deal with stopping the energy supply. The energy supply was electricity from a number of dams which supplied these factories in the industrial heartland of Germany, which was the Ruhr, still is the industrial heartland of Germany. Nazi Germany then, of course. And so one idea is to be able to, how do you destroy those dams? And so this was an attempt to use the so-called bouncing bomb, as you can see. So you have a bomb that's underneath the plane, you fly with the plane, sometimes successfully, sometimes less successfully, to be able to get the bomb, which is slung underneath it. You drop it, and you want it to be able to bounce, hence the name, the bouncing bomb, across the water. So it skips down the lake, comes to rest against the dam at the reservoir, sinks to the bottom of that dam, and then on a delayed fuse goes off. And so the rationale for that, of course, again, is related to what we understand about fluid pressure. So this is trying to get the timing roughly right for that case. You saw previously some of the timings didn't work out. Some of them bounced up and took the plane out, which of course you don't want if you're on that plane. But I think the key was that these pool balls, if you like, had to be spinning in the direction that they're traveling when they're released, so that it actually skipped the way you wanted them to, and you could actually control it so it would go where it wanted to. And I'm not sure how this footage ends, whether it ends up with the dams, but I think 2 out of 3 dams which these things were planted at were destroyed. Destroy the dam, no impoundment of water, no potential energy to go into kinetic energy to go to electricity, and then you emasculate the war effort. And so let's look at some
Almost
other
a month since the
issues
Sayana
of public trust as well. So the final one, in trying to make the case of why we might be interested in this, is some footage from Russia.
Almost a month
RT,
since the
I
Sayana
guess, is Russian
Shushenskoye power
TV.
plant tragedy,
And this is of
new
a power
CCTV
station.
footage has been made public. A
Oh.
janitor wiped
I'll shut up
floors
for a
in the
second.
machine hall just minutes before a deadly mass of water destroyed the 3 generators, burying 75 workers under the rubble. Panicked employees rushed to the exit. The rescue operation has been going on for more than 3 weeks, with the death toll rising practically every day.
Yeah, so this is the case of a dam. Someone, again, potential energy, kinetic energy, you run it through turbines in the machine hall. Machine hall sits typically at the abutment of a dam in the rock. If for some reason some of the gates fail, then all of a sudden you flood the place and you destroy the machine hall, and there's a huge amount of energy that's available to be able to destroy that. And I think this is this stuff coming out of the machine hall as you had this accident. So we need to be able to understand the roles of fluid pressures acting on structures, gates in dams, dams themselves, to be able to understand exactly what's going on in those particular cases. So that's our role. We're trying to make the case for that. Just to kind of backtrack on that a little bit, just so you get the idea of this, you know, we've talked about our reasons for wanting to understand what this behavior is, but we can do some pretty straightforward examples. So we're interested in understanding pressures on structures. Whoops. If I can write this. And it is week 3, right? Week 3. So let's just kind of take an overview maybe at each of these things. So what happens in an aircraft? And how can we use the things that we know to be able to say something about that? Well, what do we know about an aircraft? Well, you can take the cabin. We know that in the cabin there's some kind of pressure in the cabin, and outside there's some kind of pressure in the atmosphere. When you're sitting on the ground with the doors open, those are the same. When you're sitting at 30,000 feet with the doors closed, then typically the cabin pressure is atmospheric, is ground level atmospheric pressure, and this is the pressure of the atmosphere at 30,000 feet. And so what we'd like to know is be able to figure out exactly what the integrity of that structure is. It's actually something that you've kind of approached already in terms of just looking at the analysis of that. So you could do an analysis of this just by taking half the structure, right? Bless you. And if you have this structure as some kind of thickness, so let's do the calculation to see how thick this skin should be that we apply to be able to make your jetliner. It's really quite simple calculation. The thickness of the skin is T. The pressure that we have inside is the pressure of the cabin, which we call PC. The different pressure which we have acting outside is this pressure, P atmosphere. It has some diameter, which we'll call D. And we like to be able to figure out exactly how thick that skin should be. Very, very straightforward calculation. So what do we know about fluid pressures? Well, we know, for instance, that if we look at a point here, let's take this out, then the fluid pressure acting that point we know is acting in this direction, and they're both equal to PC, right? We said that the fluid pressure in a static fluid has to be acting same magnitude, all directions. And so what that allows us to figure is that not only is it acting horizontally, which we don't really care too much about, but it's acting vertically. And so we could resolve vertically to take this structure that we have here, and we're going to draw it like this. And we have this cabin pressure. We're looking only at the component which is acting vertically, which is actually the same, it's just PC. Outside we have the atmospheric pressure. it's acting in all directions, but we're only interested right now in the part that's acting vertically, which is PA. And we have this stress here, which is holding this thing down, which is anchoring this half here to its lower half, right? The force here. And that is equal to some force. And that force will equal to maybe a stress times a thickness times a length along the cabin, a length along the plane. And this is some force. Let's call this T. It's in tension, so let's call it force T. And so let's resolve this so that we look at resolving each of these forces. And so what we could do is we have a pressure here acting over some length d, the diameter of the plane. It's also, I guess, given by some length of the plane, which we'll call L. And so what's the force that's acting upwards? So we have acting upwards, we have the pressure in the cabin multiplied by the area on which it acts, which is d times L. Hello. We have the pressure outside, which is equal to the pressure in the atmosphere, again multiplied by the area over which it acts, just on this profile that we're acting vertically. And that has to equal 2 times T, right? If we wanted to, we could, I guess, yeah, so take this. So this is right? So this is the atmosphere. So let's rearrange that slightly and substitute this here, just very simply. So we end up with the pressure in the cabin multiplied, sorry. So I'm just rearranging this. This is equal to 2 times this stress that's in the metal times the thickness of the metal times the length of the cabin. Get rid of this, get rid of this. And so what we can do is we can calculate exactly what the thickness of this stuff should be if we want to be able to have the plane not fall out of the sky, basically, right? And we can put some numbers on this. This is the diameter, and we divide through by 2 times. This is the strength of the metal, which you want it at least to have that strength, and we kept this. So we should be able to check the dimensions in this. This is a pressure, units of stress. This is a strength, units of stress. So these cancel out. This is a length. This has to be a length. So we probably have our dimensions right. Let's put some numbers in from what we know. Pressure in the cabin. We said it wants to be atmospheric at sea level. So if we write that in pascals, it's 10 to the 5 newtons per meter squared, or pascals. What's the atmospheric pressure at 30,000 feet? Did it last time, right? 10,000 meters, Everest. It was about 30,000 psi. So it's 10 to the 5 multiplied by 1 minus 0.3, right? So I'm just taking this outside. Atmospheric pressure is 1 times 10 to the minus 5. Atmospheric pressure at 33,000 feet, the top of Everest. Check it out from last time. It was equal to 30,000 newtons per meter squared. Diameter of the plane, I don't know what that is. Let's take it as 10 meters. It's probably less than 10 meters in the particular case of this comet. And multiplied by 2 times the strength of aluminum, tensile strength of aluminum. We could look it up. I looked it up already. 200 times 10 to the 6 newtons per meter squared. That's the strength of aluminum. Take a piece of it, stretch it until it breaks, and that's the breaking stress that you have to apply. 10 to the 6. So we've got 10 to the 5 times 10 is 10 to the 6. So we can get rid of this and this and this. And we have 1 minus 0.3. Well, it's roughly 1, right? Let's not split hairs. So this is about 1 over 400, order of magnitude. The units of it, we've used meters, so this is meters. 1 in 400 meters. So 1 in a hundredth of a meter is a centimeter, thickness of my finger. A quarter of a centimeter, which is a 400th, is going to be 2.5 millimeters, which is, the thickness of, I don't know what thickness, well, it's the thickness of a quarter of my finger, right? So the skin that you'd have would have to be about 2.5 millimeters. Thickness. Right order of magnitude, right? I don't really know I've never measured that on a plane, but I imagine that it's certainly not a foot thick, 30 centimeters. It certainly probably isn't microns thick, like tin foil that you use to cook your chicken on the barbecue, but I can imagine it'd be a couple of millimeters. Seems quite reasonable. So what we've done unwittingly is we've made some assumptions about what's going on, and we've looked at a fluid pressure on structures. That's really all we're attempting to do. We're trying to calculate what those pressures on structures would be so that we can make some useful evaluation of it. In this case, well, you probably want a safety margin, so let's make it 5 millimeters thick, and then we think we should be able to fly quite safely. Okay? And so that's what we're attempting to be able to do in this particular part of our class. So unwittingly, we've done a very simple calculation. We've kind of assumed, if you look at the free body diagram for this, we've assumed that we have this arch. We have acting here a distribution of fluid pressures, which is this magnitude is the cabin pressure multiplied through by the diameter, and also multiplied through by the length. And so what we've calculated is a magnitude of, if you like, it's a resultant force, which is equal to the area times the pressure. And the area in this particular case is equal to the diameter times the length, and we've added to that, multiplied by that, the pressure. So that's kind of what we've done. So we've looked at fluid pressure at a point up here. We figured out we can cut a free body diagram to look at what the distribution is on this lower contour, which has to be the same as you apply on this curved surface. And we've just multiplied the pressure by an area, and we've used that as a resultant force, and we've used that in some useful way to be able to figure out the stability of this particular shell structure. Very, very straightforward. So what's been easy for us here is that this is a gas, right? It's a gas in here, and so the pressures don't really change very much as we go up and down in this, and so we can write it as a straightforward pressure distribution. If we look, for instance, at the fluid pressure behind a dam, when we're dealing with a liquid, then we no longer have that luxury.
I have a question.
Yes, go on.
In the first line of the first equation line, did you get two T's left?
Because you're pulling down on this side and you're pulling down on this side. Okay?
Two sides.
Yeah, two sides of the thing. You cut it in half, and we're pulling down on both sides with this canopy above us. So, okay? Any others? Okay. Good question. So we talked about, well, a couple of those things were about dams, right? You've seen Europe, no, not, I guess, Vacation, right? The dam tour, the dam tour, Chevy Chase. Seen that? Well, fine. Very simple dam. Let's draw it the other way. So this is the dam. So this is physically the structure of the dam that we have. And so if you wanted to plot, for instance, the fluid pressure and how that changes with depth, I won't call this Z, I'll call this Y, because remember we've resolved to use this right-hand coordinate system, X, Y, Z, vertically upwards, but this is where we take a deviation from that maybe. So this is physically the dam. And we know that the fluid pressure behind that has to be equal to, the pressure is equal to the unit weight of fluid times the depth, right? Up here the depth is 0, so the pressure is 0. Down here the depth is y something, so the pressure is something. And so in this particular case, instead of the pressure being uniform with height in our cabin, now it changes. And it changes because it's a significant unit weight that we're applying here. And so the reason for the dam busters, of course, right, is that if you have a bomb that hits the dam here, it explodes. This is air above here. All the energy gets pushed into the air. We know that the amount of force you could apply on a dam is equal to mass times acceleration. So what you want is something with mass in it that reacts against it. Mass of air is very small, so you have something like here, and you get a little blip in the, maybe you get a little blip in the pressure that comes here, and it tickles the dam. Okay, I can get rid of that. If you put it down the bottom, all of a sudden it's confined, and so the pressure you might expect to get from that would be actually a much bigger augmentation rate to it. So it's a bit macabre to talk about these things, but that's kind of the rationale of it. You want to have some confinement around it so that it does something, and I'll let you follow up with this if you want to look at it. There's certainly newscasts of the dams. I think 2 out of 3 dams completely breached and no water left behind them at all. Horrible loss of life downstream for people, but part of the way it goes. And the reason to have the dam the bomb sitting at the bottom of the dam is you want to be able to have some reaction against it. So that's kind of peripheral to what we're talking about. But what we'd like to do is to be able to figure out exactly what, under normal circumstances, the service life of these dams would be. And you want to be able to construct the dam so it doesn't fall over. And so in the most simplistic sense, what you could think of in terms of the design of a dam is this very simple, I'm not doing very well, is this very simple arrangement to be able to look at, again, I'm just drawing the same figure. This is the dam. This is the fluid pressure distribution behind the dam. This is going to be our y-coordinate system down here. And this is going to be our fluid pressure. And so what we'd like to do is be able to figure out, and when we talk about fluid pressures on structures, there are really only three things we'd like to know. Certainly, we'd like to know what the magnitude of this resultant force is, which we'll call F uppercase R. So it's the resultant of the force that's applied by this pressure distribution. We'd like to know that. We would also like to know where it acts, which we'll call the location of this resultant, Y sub R. And so we've already done this, right? We've done this for a simple example. We've got the resultant force that acts. It's just equal to the area times the pressure, which was uniform in this case. But now we want to deal with cases where the pressure distribution changes with depth. And so we've got to do something else in addition to that. So we've got to do something a bit more complicated. And so it turns out that what we would like to be able to do is we'd like to be able to figure out exactly what the moment is that we apply to this structure to be able to represent that. And our reason for doing that is basically this. We know that, for instance, for these three things, sum of the forces equals the magnitude of the force. So FR is just equal to the sum of all the forces. But what we can also write from this is that the moment applied by this pressure distribution is going to be equal to the sum of the forces multiplied by resultant, right? So in other words, if you take this force acting here, you take the lever arm through which that force acts, then the net moment from that has to equal the product of these two. You could think about it being applied in reverse so that one's acting against the other one, but really what we're saying is that the moment is just equal to the resultant force. We could also write this as this, I suppose, times the lever arm through which it acts. Force times lever arm gives a moment. And so the reason we want to also use this expression is that we think we can get this resultant force pretty easily. We did it for the aircraft fuselage straightforwardly, just by doing an integration. So if we can figure out what this is, if we can also take this force distribution and calculate what the moment is, this one, then we can figure out exactly what this unknown quantity is. So we'd like to know the force, which we can do just by what we've done already. We'd like to know the lever arm through which it acts, because that gives us the location where the force acts. And so we'd like to know the force magnitude. We'd like to know where it acts. And thirdly, use this to define stability. And so I'm thinking in this particular case, for instance, if we have a dam that has a weight here, and let's take a point about here. We have a resultant. It's of some height h. It's of some width w. Getting a bit more complicated than I really wanted to. But if we know what the resultant from this fluid pressure is, and we know where it acts, we can take moments about this point here, and if this is this actually is 2/3 of W. I won't tell you why that is the case first. So we can take moments about this. So the moment acting in this direction is this weight multiplied by the lever arm. So the weight multiplied by 2/3 times lowercase w. Let me just do this so it's clear. And for this to be stable, then it has to equal this lever arm, which is going to be h minus yr, multiplied by the resultant. And so we want this to be so that this number is bigger than this. It'll be stable, right? All we're doing is we're looking at it rotating around that base. And so long as this number is larger than this number, it'll be stable. So what we can do, we know this. We want to choose what this is so it's stable because we know what these other components are that we can define. So we can define the conditions by which it acts. So I'll reiterate this again. There are three things we need to know in this segment. We want to be able to figure out what the resultant force is that's acting. We want to be able to figure out where it acts. And to do that, we can take moments about anywhere in the structure. You can take them about the top here, or you can take them about the bottom here. It doesn't matter. You'll get the same result for the location. And then, once we know what the force is and where it acts, we can say something about a failure mechanism, in which case we have to specifically choose the failure mechanism, in this case saying that for this dam to fail, it's going to rotate about the toe, and therefore we have to take moments about this point. If we take moments about this point, it will say nothing about the failure mechanism. Right?
Question.
Yes. So those 3 points are important. Yes.
So in this case, because all our forces are directed essentially along the x-axis, x sub r would just be along the y-axis, just because of where it is. Is that correct? As far as we know, if we want to look for x sub r.
What is x sub r? We have y sub r.
Correct. But if, in this case, because all of the...
Yeah, we're only resolving horizontally. Well, this would be... This length here would be an x sub r, kind of, but it's the x sub r for the weight of the concrete.
If we had a situation where all of the pressures were not directed in the exact same direction, would x sub r come into play?
Yes.
Okay.
Yes. So we'll do it that way. Okay? So,
Question.
yes.
And then For that equation to make sense, the last one, you have y sub r, and then you need to match that with a certain gradient, which you said was 2/3.
Yeah, so you can imagine that if we made this dam so it looked like this, then what physically that would mean is that this force Fr still acts at the same place and it's big. This weight of the dam, let me redo that. It would act at this point, and this would be a big Fr. The weight of the dam would act here, and this would be a small number. And the resultant of these puts this vector that's outside the toe, physically what it means. If you make the dam bigger, then nothing's changed here. Fr is still the same. The weight, I guess, would be much bigger now. So this weight here would now be much bigger. And the resultant of these would be that the resultant would not go outside the toe. Right? That's basically physically what's going on. Right? If the resultant of the forces goes outside the toe of this dam, then it falls over. If the resultant of the forces is inboard of this point, it's stable. If it's outboard of this point, it's unstable. Hence, you want to be able to choose that. So don't get hung up in this. Understand those three things. We want to know the resultant force, we want to know where it acts, and then we want to be able to define a failure mechanism is kind of typically what we want to be able to do in this case. Okay? Everyone still on board? Okay. All right. So we won't do the derivations which are in the book, but we will kind of follow how this works. So here's the geometry we have. So think of this upstream face of the dam as what we're drawing here. So this is the pressure distribution. Stop it. I'm sure you can draw this much better than I can. So this is the chain. This is basically pressure equals unit weight times y. We're going to call this location here y equals y0. We're going to call this location here y equals y1. We're going to have a width to this. We're going to have this height here is going to be equal to a little bit of y, dy, which is also going to be this band that goes across this plane. And so this band here is also equal to dy in thickness. And if you like, this volume here is going to be equal to width times dy, right? This is just the area of that little band, nothing more than that. Let's call that dA, not the small slither of this. And what else do we want? And so this here is equal to P times dA. So this force here, I ran out of space, but this equals pressure times dA. Pressure times an area is equal to a small piece of force. So instead of doing what we did before, which was just kind of taking a magnitude, multiplying it by an area to get the force that's acting, let's do it kind of calculus-based. I know that's a dirty word, but let's use it. We're going to do exactly the same thing. So we're going to calculate the resultant force, F sub r. The resultant force is going to be the sum of the fluid pressures times the area, right? Pressure times an area is a force, nothing more than that. This is the incremental piece of pressure we have applied on this area, so that's an incremental piece of force. And what we're going to do is we're just going to sum those up as we go down in all these stripes as we go down through this. And so how do we write that? Instead of writing it as a sum, we take it as an integral. We take it as a fluid pressure. We take dA as equal to the width times dy. We integrate it between the two limits. It can be this, the top of the distribution and the base. What else do we know? We know that the pressure is equal to the unit weight times y, which we can substitute. And so if we do those substitutions, we have the same limits between the top and the bottom. And by the way, so this is a plane which is going vertically down. It's intersecting the free surface here. So this is, if you like, is air above and water below. And so, if you like, this is our plane. And we don't see this online. This is our coordinate system. Y is my finger. X is my thumb. The thumb is on the surface going across. And we're interested in the pressure that's applied on this plate, which is going to be increasing in depth. And so all we're doing is we're summing up each of these individual forces as we go down to figure out what this maximum resultant is. That's all we're doing. And so if we substitute for this, should use the sharp end of the pen. Unit weight, y times y dy. And if we do that integration, what do we end up with? We end up with a half y squared, right? So unit weight times w times a half y squared between these limits of y0 and y1. If we take y0 at the surface, then this is equal to 0, and this becomes unit weight of fluid, the width times a half y1 y1 y squared. I just chose to write that this particular way because I feel quirky about it. And so if we want to rearrange that, then let's rearrange it so we have it written as, let's take these two terms together. So width times y1 multiplied by unit weight times a half y1. Seems like a stupid way to write it, of course, but let's write it in a slightly different way. We can write it as an area multiplied by a unit weight multiplied by the y-coordinate of the centroid. Okay? This is, well, if we go back to our notes, this is one expression you should put away in your mind. It's always true. It gives you the magnitude. This is the force that's applied on a plane structure. So plane structure is a bit of a fancy word. On a flat plate. Of course, if you put this in water, there'll be that force on one side, the same force on the other side, so there's no net force and it stays where it is. But the idea is that if you know the area of your structure, this is the area. If you know the unit weight of your fluid, and if you know the vertical depth of the centroid, so this is the depth of the centroid, of the plate, then you have the solution. So what's the depth of the centroid of this plate, right? You take Pennsylvania, you get where State College is, right? Equally inaccessible to all. Draw a point between Philadelphia to Erie, and the other way, State College is right in the middle. We're basically at the centroid of the state. But the centroid of this plate is the place which would be the balance point of this piece of paper, if it didn't bend, that would sit on my finger, and that's the centroid of this physical plate. Not the centroid of the pressure distribution, but the centroid of the plate. So if you put this plate below water that's this deep, the depth of the centroid from this point is whatever the separation between my two hands is right here, and you always know that. It doesn't matter if the plate is like this, or like this. This equation still works. It gives you the magnitude of the force that acts. Importantly, the magnitude of this force does not act at the centroid of the plate. This force acts at the center of pressure. I'm just going to write it in English, RE, center counting, center of pressure, which is not equal to the centroid of the plate. So this is a universal expression. It's rigorous. We can get the magnitude of the force. We just need to know the area of the plate, the unit weight of the fluid, and the depth of the centroid. The vertical depth of the centroid below the free surface, where zero pressure atmospheric acts. Okay? So that's the first thing that we have to know. And of course you can get that centroid just by folding it like this. By folding it like this. Well, we can't see this on the movie, can you? And the place where those intersect is just this point right here. Right? Nothing more than that. So, how are we doing? We said we want to figure out three things. We've done the first of these, right? We figured out what the magnitude of this resultant is. We'd like to know where it acts. So, that is a bit more complicated, and it's going to take us longer to do it than today.
Can we scroll back down?
Yes, let's spend some time on this. To where? Back down to this?
Yeah.
Okay. Just to write things down or for questions? So it didn't get quite as far as I hoped, but so let's reiterate those three things. Have you got them? Can you tell me what they are without me showing you? I'm fine if that's the case. Need to know what the magnitude of the force is. The last expression we got gives us the magnitude of the force. We want to know where it acts because we want to be able to figure out how it fails. We don't know how to do that yet. And then once we know where the force acts and the magnitude of the force, we can figure out whether the structure fails or not. That's basically what we're trying to do. Okay? I'll leave it at that.